All right, so good afternoon. We're gathered here because we recognize the importance of invariance and symmetry in universal science. Accordingly, my talk today is about the power of invariance in terms of its potential to act as a unifying construct for all of cognition. Invariance, as you know, has many guises. Sometimes the construct plays a direct and central role in theory formation, as is the case in the work of some of you here and my own work. Other times it assumes a more covert and modest role. My proposal today is that it should assume an overt and central role. So much of my talk today will be based on my recently published book entitled Mathematical Principles of Human Conceptual Behavior. Note that given the amount of material that I would like to cover, in 35 minutes, I will try to deliver the most efficient talk, so I will ask you to hold your questions for after I am done. So invariance and symmetry principles often take center stage in the physical sciences. Intuitively, invariance refers to the condition of remaining the same in some key respect, in spite of having been transformed or perturbed in a particular way. Essentially, invariance reveals hidden patterns in an efficient manner. Accordingly, groundbreaking and precise theories and laws in physics, chemistry, and mathematics are based on invariance principles. In fact, it would not be an exaggeration to say that the most successful theories in the history of the physical sciences are based on invariance principles, such as the theory of relativity and Maxwell's theory of electrodynamics. So Einstein knew it, Maxwell knew it, Poincaré knew it, Lorentz knew it, all the great physicists knew it, and most mathematicians know it. So why has the science of the mind and brain not been systematically built directly on invariance principles? Perhaps because of the spatial bias, that is, symmetry is too often associated with spatial intuitions. Generalized invariant structure theory provides an alternative direction, one that is abstract enough to generalize well to a wide variety of cognitive phenomena, and that can precisely make predictions about important aspects of human cognition. Today I will propose such a direction. So undeniably, invariance constructs have also played a role in the cognitive sciences, most notably in Gibson. In his research on vision, he argued that the momentary retinal image is the wrong level of analysis. Instead, it is the invariance in the transforming patterns of stimulation of the sensory system that specify the relevant properties of the environment. In short, humans directly detect the key structural information from the environment. On the other hand, Garner proposed that goodness of pattern judgments could be predicted in terms of rotational symmetries. Finally, Lighton posits that the mind assigns to any shape a causal history explaining how the shape was formed. By examining the shape in terms of its inherent symmetries, he argues that symmetry is a key component to cognitive processing. In addition, there have been several researchers that have explored perception from the standpoint of invariance and symmetry. This include Pislow, who's here today, Wagemans, and Palmer. However, these efforts have been in specific areas of cognitive research, and no systematic attempt has been made to link the various cognitive capacities using invariance principles. So next I will demonstrate how I model concept learning and classification performance with a particular notion of invariance referred to as categorical invariance. But first, for the initiate, we define a concept as a mental representation of a category of entities that determines membership in the category. Thus, researchers measure concept acquisition by observing categorization behavior, namely how well observers classify members of the category of entities, that is, the categorical stimulus, from which the concept is learned, how long it takes, on average, to make classification decisions, and in terms of difficulty judgments. In other words, learning difficulty judgments, classification error rates, and reaction times operationalize concept learnability. Also, I should say that in an attempt to model concept learning, researchers have hypothesized how these are mentally represented. Of the three major representational paradigms seen here, rules and prototypes act as information compressors. Only the exemplar account does not seem to involve a compressed representation. I will later argue that ideotypes, the core representation in GIST, is what the exemplar view should have been in the first place, and that prototypes and rules can be generated from ideotypes. So research over the past 60 years has shown the existence of robust learning difficulty orderings for structure types defined over binary dimensions. Each category structure type is determined by the relationship between the dimensional values of the objects in the category. And you can see in this Boolean cubes those relationships. For category structures defined over 3 dimensions, these relationships between dimensional values can be expressed in terms of the coordinates of each object stimulus in a Boolean cube. Category structure instances may be generated by rotations and reflections of the Boolean cube. For example, there are 6 instances associated with structure 1 here. You can think of the possible rotations of the cube. But these numbers really do not predict learning difficulty. So we're not looking at invariance and symmetry at this level because it doesn't work. So such relative difficulty between categories measured in terms of classification accuracy or difficulty judgments tells us something fundamental about our conceptual system, namely which relational structures humans are most sensitive to. So here we show a specific family of category structures, again, that some here may be familiar with, the 3 to 4 family. That is 3 binary dimensions with 4 objects, whose structures are defined over, well, as I said, 3 binary dimensions on 4 objects. These categories are of particular interest because of their dimensional size and cardinality. That is 3 dimensions defined over 4 positive examples or quantities that are tractable for humans. They are also of interest because when people are tested on these categories, the results show a robust ordering in terms of their difficulty. For example, when looking at mean errors from classification tasks, type 1 here, this categories are the easiest to learn. Type 2 are second easiest. These 3 are about the same degree of difficulty. That is, there's no statistical significance in performance on these 3 category types. And finally, this is by far the most difficult to learn. So this empirical result has been replicated many times by multiple researchers over the last 55 years. In my lab alone, we've replicated it 18 times. But it has resisted prediction and explanation. Only the generalized context model by Nosovsky can predict it, but it takes 13 free parameters to account for 6 data points. So now back to GIST. Well, actually, I want to point your attention at second learning difficulty ordering with respect to the 3 to 4 family of structures. So when these are defined over the integral dimensions, such as hue, brightness, and saturation, we see this ordering instead, which is, as you can see, very different from the separable dimensions ordering. So we're going to show how GIST perfectly accounts for both orderings without free parameters and for the ordering of an additional 78 category structures. So generalized invariant structure theory, or GIST, is a mathematical theory of concept learning based on the core principle that when presented with sets of objects in the environment or exemplars in the mind, observers are categorical invariance pattern detectors, and that the associated categorical invariance pattern detection mechanism that makes categorical invariance detection possible is a necessary precursor to the formation of concept representations such as rules, prototypes, and difficulty judgments. And as you can see, the key construct in GIST is categorical invariance, so I shall explain what I mean by it. And what I mean by its core representation are referred to as an ideotype. So let's see be a non-empty finite category of objects defined by binary dimensions as shown on the left side of these arrows. So here we, okay, my pointer again disappeared. So here, think of this 3-object category. Okay. So this is the original category that we are going to perturb. So we can perturb any such category systematically along the dimensions that define the category to obtain a perturbed category T sub I of C. In the examples shown, the dimensions are color, shape, and size, although they can be any dimensions that are relevant to the observer. And by the way, yes, the dimensions need to be known by the observer, but this is not a problem. We brief subjects, and they tell us precisely which dimensions, including children, in fact, which dimensions are at play. We have multidimensional scaling to determine what the number of dimensions is. We have other techniques, so it's not an issue. They do know that the dimensions. All right, so once the perturbation takes place along each of the dimensions, here on the dimension of shape, here on the color dimension, and here on the size dimension, the next step is to determine the elements that the perturbed category has in common with the original category. So the proportion of this categorical invariance, in other words, those objects that are able to survive the perturbation, form can be arranged in terms of this vector, and this vector is known as the structural manifold in the theory. Okay? Now, the question is, what does it all mean? So, in GIST, structural manifolds are quantitative descriptions of concept meta-representations in psychological space referred to as ideotypes. So structural manifolds may be defined in a number of equivalent ways, modeled theoretically, set theoretically, analytically, and you can find these equivalent formulations in my book. This is the analytic formulation here in terms of the partial Boolean derivatives. But you can also do it in terms of model theory. And again, I refer you to the cited works for you to see how that works. So the value of each of these components of this vector of the structural manifold are referred to as kernels. And the structural kernels, what they do is they contain information as to the degree of redundancy and or diagnosticity of each dimension. So the value of each structural kernel represents the degree of local invariance and also represents the degree of redundancy on a direct scale and or diagnosticity on an inverse scale of its corresponding dimension. So for example, if we preserve all the objects, this would have a value 1, and that would be a totally redundant dimension. It may preserve only a fraction. In this case, 2/3 of the objects are preserved, so that's 2/3 degree of redundancy. And on an inverse scale, it would be a 1/3 degree of diagnosticity. So one of the core ideas in GIST is that in order to form rules for the purpose of generalization and hence classification, humans must first extract the key or most diagnostic features of the categorical stimulus. And these are determined by their degree of relative invariance as characterized by the structural kernels. So one important principle in GIST, the invariance parsimony principle, states that dimensions with degree of local invariance of 0 and 1 are given priority in the rule formation process. So the most random dimensions, clearly, because those can be discarded or ignored. The most diagnostic, because you have to have those to form a rule. Okay? The stuff in between is not quite as important to human observers. So as mentioned, ideotypes are memory traces of the key structural information, namely invariance information of a categorical stimulus. So applying the Euclidean distance metric yields the norm of the ideotypes, which represent the overall or global degree of invariance of categorical stimuli. This degree of invariance can be construed as the overall coherence or relative homogeneity of the categorical stimulus from which a concept is learned. The direction of the ideotype, so these are plotted, these are ideotypes, but they're plotted, they're described quantitatively, the location in psychological space or invariant space by the structural manifold. Okay. So the distance between each of these ideotypes and the zero ideotype, which contains no invariances, right? That represents a situation where each dimension is fully diagnostic. Okay. that distance is the degree of invariance. So you take the norm of these vectors and you would get degree of invariance. Overall degree of invariance or global invariance. And again, this can be thought of as the coherence of the concept or the categorical stimulus. So the direction of those vectors also contains information. It represents the nature of the qualitative information in the categorical stimulus in terms of the structural role that different dimensions may play. So the permutations of the structural manifold generate a set of vectors associated with the idiotype. All right, so the invariance model that links idiotypes to concept learning difficulty and or category complexity is seen here. It has been empirically and theoretically demonstrated to be a strong candidate for a law of conceptual behavior using a plethora of historical and new data. The model states that the learning difficulty or subjective complexity of a categorical stimulus, X, is inversely proportional to the exponent of its degree of categorical invariance squared and directly proportional to its cardinality. So you see K here. This is a scaling parameter that can be interpreted as a discrimination parameter for concept structures. We'll revisit this core model later in the talk. The version below, this one with the single parameter, this one is non-parametric. And it uses a discrimination index based on a baseline standard of the smallest non-trivial number of dimensions, which is 2, divided by the number of dimensions on which a stimulus is defined. And that's what this is, yeah. Okay, so the model, that particular model not only does it predict the 3 to 4 family ordering, but as can be seen here, data from an experiment involving 84 category structures across 5,100 unique structure instances. And this includes, by the way, the 3 to 4 category structures, or that family of structures, was fitted with unprecedented accuracy by the invariance model without free parameters, actually. So here we have, you see the fits to the invariance model with parameter, with the scaling parameter and without parameters. Again, extensive bootstrapping was conducted involving tens of thousands of samples of 10, 20, and 30 data points with extremely stable results as reflected by R-squares. So the R-squares remain the same across the board. About 90% of the variance accounted for all these bootstrapping tests, which is a good indication that there is no overfitting or that the fitting of the data is not, by chance. So compared to other models, how does it do? Well, you can see here that the leading contenders don't do nearly as well. We see that the number of mental models model accounts for 66% of the variance, the minimization complexity for 61% of the variance, algebraic complexity by Feldman, 57% of the variance. Here you see the distribution of the residuals, and you see how nicely, this is very nicely Gaussian in the case of the invariance model. So also, as can be seen here, without free parameters, the candidate, this particular, the invariance model accounts for significantly more variance in the data than a recent entropy model based, or a model based on entropy, on Shannon Entropy, referred to as the information complexity model. That was recently published in Mathematical Psychology. It's interesting because these researchers didn't actually show this graph. They didn't want to. Instead, they show fits within category families. And those fits, turn out to be pretty nice. But when you put it in the perspective of all the structures, then they don't do nearly as well. And also, when you do bootstrapping here, this thing falls apart. The R-squares does, it's all over the place. Okay. So, but how do people detect categorical invariance? If the previous mechanism seems psychologically implausible, although it may still be what actually happens in the brain, we can interpret it in terms of a new kind of similarity assessment and goal-directed attention process. This has the added benefit of generalizing categorical invariance to continuous domains. The mechanism is referred to in GST as dimensional binding. Dimensional binding constrains similarity assessment in a way that is equivalent to the process of extracting invariance patterns in categorical stimuli described in the previous slide, or in the, when that perturbation mechanism in a few slides ago. More specifically, perturbing a dimension of a pair of object stimuli in a set, and determining whether the generated pair of objects remain in the set is equivalent to determining after a dimension has been bound, that is completely suppressed, whether the two distinct objects in the set are identical with respect to their free dimensions. So it's kind of relative similarity. If so, then they are categorically invariant because the only way they can otherwise differ is on the bound dimension via the binary perturbation. Thus, the determination of invariance is equivalent under either process. We refer to this relationship as invariance-similarity equivalence principle. This principle is easy to prove. For a proof, you can see me after the talk. Furthermore, by weakening the partial similarity condition on the right side of this equivalence. So this can be weakened. So it has to, it may be approximately, this could be approximately equal. In other words, they're similar rather than identical, right? Gives a more flexible way of construing the perturbation and determination of invariance on the left side. Okay. Thus, abstract symmetries emerge that were not initially detected. So these are the invented symmetries that Don talked about yesterday. In reality, these are approximated symmetries. This is done by a human observer when his sensitivity to differences between dimensional values and consequently exemplars decreases. And the mechanism of dimensional discrimination changes distances in psychological space which determine partial degrees of similarity. The different levels of discrimination are controlled by a distance or discrimination threshold, tau, that allows for the generation of different ideotypes and therefore structural manifolds for the same categorical stimulus. The mathematical description details of the binding mechanism, systematic goal-oriented attention shifting, and partial similarity assessment may be found again in the cited works. And yes, there is actually a proof of when you weaken similarity here, instead of identity, you weaken it to approximately similar. There is a proof that this is still equivalent to a specific kind of transformation on this, a way of defining the perturbation transformation on the left side of the equivalence. I'd be happy to share the proofs with you at the end. So this is just a measure of a way of expressing partial similarity after suppressing a dimension. And here we have relative distances and the relative similarity matrix that is generated with the assumption that observers are making these comparisons, pairwise comparisons in the stimuli. And this is a measure now of degree of local invariance. So this is a little bit different from the original measure because we've included this discrimination. Here it is. So the similarities that we're adding up, they have to fall within that tau. The tau that determines the interval between 0 and tau here. So those distances have to conform to the threshold, and then we can add the similarities that are consistent with those distances, and then we get a quasi-manifold, because it's not quite, right? We're not capturing really the perfect symmetries, but weakened symmetries. So the plausibility of the binding mechanism should be questioned. So how cognitively plausible is the proposed binding mechanism? In an eye-tracking experiment conducted in my lab, we found fixation patterns consistent with binding. Particularly in this graph, you see for each category structure of the 3 to 4 family that there are 3 1-second intervals on each graph where the dimensions change roles and for which most of the fixation time is allotted to 2 of the 3 dimensions. This is one particular case. There are 2 per graph. And this is, this is not really conclusive. A lot of work needs to be done, but at least there is some evidence that it is plausible that human observers are doing this. I mean, we do see it, for example, here you see the suppressed dimension, so there's hardly any fixation on that, but then these 2 are very active. These other 2 dimensions are active. So from these considerations, we can conclude perhaps that dimensional suppression is a form of perturbation. Now here we see the invariance model once again, but this time with the more general notion of categorical invariance represented by the R capital phi, where the degree of constabulary difficulty of a categorical stimulus x is directly proportional again to the cardinality of x and inversely proportional to the exponent of its degree of categorical invariance. That is the idiotype length as square, and below is the free parameters variant. Now, but why does the invariance model have an exponential form? The exponential form follows directly by applying Shepard's exponential decay similarity law to determine degrees of similarity, albeit at a global category level, between an idiotype, namely the zero idiotype, right, and any idiotype in the space. So it follows directly from that. Now remember, the zero idiotype, which stands for a structure with no redundancies or zero invariance, a structure that has fully diagnostic, the dimensions of which are fully diagnostic. Second, it makes accurate predictions, as I mentioned, accounting for about 90% of the variance or above. In the data from large-scale experiments, the fits to the data are remarkably stable, as I mentioned earlier. And finally, and the data is not being overfitted from all tests that we've conducted. The exponential form also can be derived in the style of psychophysics from invariance principles. So we did conduct psychophysical experiments in which we asked for difficulty judgments on category structures as well. And we were able to derive the law from those psychophysical experiments. I call it a law. It's not a law. It's a candidate law. It's a model of, it's an invariance model for now, but it's a candidate law, I believe, of invariance. So one thing that you also should note here, that it accounts nicely when you use that tau discrimination parameter, when we're looking for perfect, when we are restricted to perfect symmetries. What we see here is we get in the perfectly in the separable ordering, dimensions ordering. In other words, this is the Shepard et al. Result, 1961, right, that I presented earlier. And here we see that the integral ordering is accounted for perfectly when we said tau equals 1. So the invariance model can also predict the learning difficulty of acoustic concepts. Here we see how nicely performance on both acoustic concepts and visual concepts, how nicely they're correlated. This is at the instantiation level, at the category instance level, and this is at the structure level. This is for category structures involving 2 dimensions. So we're not restricted to visual domains, right? We can do this acoustically and gustatorially and olfactorily, and it seems to work. So in short, I want to conclude this section of my talk with a brief list of key developments in GIST. GIST provides a simple measure of the overall degree or global degree of invariance of a category. It introduces a direct geometrization of degrees of categorical invariance. It provides a generalization of categorical invariance to continuous and n-ary dimensional categories. It is useful in deriving cognitive models in other domains from a few invariance principles. It provides a cognitive mechanism for invariance detection in terms of attention shifting and similarity assessment. And it provides the most accurate theory of classification behavior up to date without free parameters or with a single free parameter. Yes? Okay. So now that I have demonstrated some key features of GIST, I wish to revisit the ultimate goal of this talk, and that is the idea that we can, by using models based on invariance principles as a foundation for cognitive research, derive other models from this, and build a system whose inner consistency can be tested by the fits to the data at each level of derivation. So using the garbage in, garbage out rule, we know that whenever a fit is not achieved by a derived model, it is because either one of the founding models is invalid or because one of the related constructs is confounding and not related as hypothesized to the constructs comprising the core models of the system. So as an example of this process from GIST, the GIST stem and its variance, that is the core GIST model, and its variance can help us derive models with respect to these other capacities. Okay. So my graduate students and I have tested these models over the past few years. All models account for about 90% of the variance or above, a level of performance as good or better than anything we have put these models against. So also this interconnectivity is evidence of the mutual stability between, I think, anyway, the models, and therefore that the original model of invariance in which they are based is a solid foundation. So I want to briefly, very briefly, go over them. First, I want to talk about this measure of representational information. So using, whenever you see, by the way, this red outlines, boundaries, what that means is that is an instance of the invariance, the core invariance model. So here is a definition of representational information. Essentially what this says is that the representational information that's carried by a subset of a category of objects can be expressed in terms of the rate of change of the complexity in the complexity of the category. Okay. And again, we have obtained remarkable fits using this new characterization of information as the rate of change of complexity. Okay, so here's another one. This is a model of attentional fixation. So we wanted to predict fixation on eye-tracking tasks. And what we discovered is that there is this inverse relation between the average fixation time and the amount of representational information conveyed by an object with respect to its category of origin. So this model states that the average fixation time on an object from a set of objects is inversely proportional to its amount of representational information, as described by the measure that I showed you in the previous slide. This model links goodness of pattern judgments to the degree of invariance pattern detection in a set of objects. More specifically, perceived goodness of pattern is directly proportional to the degree of categorical invariance to some power. The model makes near perfect predictions regarding people's ratings on the degree of goodness of pattern of acoustic and visual sets of objects. Finally, I want to show you this result. So Vigo and Doan tested this model of choice reaction times, which states that the choice reaction time of an object R in a category of objects F is directly proportional to the sum of the square of the degree of categorical invariance of the category F and the log of the cardinality of the category F. Again, without free parameters, we see remarkably accurate fits to the reaction time data. We also see that it performs much better than the leading contenders. Hicks' law, for example, and the suppression of aspects model by Tversky. Here we see how the later accounts for only 23% of the variance. So we're accounting here for the role that the structure, not just the number of items, but the structure of the various categories, what that contributes, the invariant structure to the processing of the category. Okay, thank you. So I'm going to wrap up here. So due to its generality, this has been found useful in tackling difficult problems in several other fields. These include data science, clinical psychology, neuroscience, AI, and social psychology. In data science, we've developed a technique known as structural manifold analysis, where we can extract the most relevant features from large data sets. And it has performed quite well so far. We'll see what the future holds, but it works as certainly a feature extraction technique in data sets. In clinical psychology, we studied ADHD adolescents, and we have found also that it does extremely well in distinguishing between children with or adolescents with ADHD versus those without ADHD. In fMRI studies published in Brain Research and Neuroscience Letters, these researchers cite GIST as a way of explaining the results. And in conclusion, I have given you a brief introduction to GIST and to the power of invariance. We still need a large body of replicated empirical data to further corroborate the introduced models and to corroborate newly derived ones. However, I hope that this does not deter researchers here from using the proposed invariance-based framework to make sense of cognitive phenomena by establishing well-motivated links to the proposed constructs and candidate laws. Indeed, our theoretical results are only as good as the foundation upon which they are built, and there is no better foundation than one based on invariance principles. And this is my group of researchers in my lab. So thank you very much. So yes, I am open to questions. Yes?
I was wondering, on one of the slides you had dimensional suppression as a form of perturbation.
Right.
In thinking about how attention gets started maybe by some aspect of the stimulus, and keeping in mind that a lot of cortical processing, cortical column processing is inhibitory, is this consistent, do you think, could it possibly be consistent with the idea that once there's a difference, a detected difference in one of the stimulus components, that starts a kind of, I don't know, spreading activation of inhibition, where you get that, you saw the eye tracking went down, so there's an active suppression of one component while attention is directed to the two.
Well, I think it's easier to find consistency between that neuronal picture, right, and this idea than it is, in terms of the perturbation mechanism, the original one that I showed, which does a lot of the work. I mean, we don't have to really go beyond this for the data to be fitted. But if we want to start dealing with continuous cases, we do have to, I think, relax or weaken identity on that equivalence principle. So I think that's going to be far more easier to make sense of for neuroscientists, this idea that suppression is a kind of perturbation, than to buy this other story, right, of this complex, this sort of, this transformation that maps features to opposite features, right? So